Today we're going to look at percolation centrality, a measure of the importance of nodes in directed networks where a contagion is spreading. We'll first look at some motivating ideas, and then we'll derive the percolation centrality formula. Next, we'll build intuition by analyzing some special cases. Finally, we'll look at how percolation centrality can be applied to real-world contagion spread. Before we begin, for the purposes of this video, when we have an edge that has an arrow in both directions, it stands for two directed edges, one going in each direction. Let's consider a virus spreading through a connected, directed network of people. Each person is modeled as a node, and if a person A can spread the virus to a person B, we draw a directed edge from A to B. Intuitively, in this scenario, we might think that nodes that lie along the most shortest paths with infected or percolated source nodes, such as nodes 3 and 10 in this example, would be important to the spread of the infection. From this point on, we'll refer to paths with percolated source nodes as percolated paths. One way we can define the importance of a node V based on these ideas is as follows. Defining a percolated pair to be an ordered pair of nodes where the first node in the pair is percolated, at a fixed time t for our network, we can sum over all percolated pairs of nodes, SR, that do not include our node of interest, V, the fraction of shortest paths from S to R that pass through V. In our formula, sigma sub SR of V is a number of shortest paths from S to R that pass through V, while sigma sub SR is the total number of shortest paths from S to R. We'll call the result of our sum C of Vt, for centrality of V at time t. This is not yet the true percolation centrality, but it's very close to it, and you can see how it's based on our intuition from earlier about important nodes intercepting many percolated paths. We can get the same result if instead of summing only over percolated pairs, we sum over all ordered pairs of nodes in the network not including V, with each summoned multiplied by the quantity x sub s of t, which we define to be the percolation value of the node S at our fixed time t, where the percolation value is 1 if the node is percolated at time t, or 0 if it's not percolated at time t. This has the effect of setting equal to 0 all of the summons corresponding to pairs without percolated source nodes, so it achieves the same result as summing the shortest path fraction over only the percolated pairs. One thing that makes our metric useful is that it updates over time as an infection spreads through a network, which we can see in this example. However, there's a problem with the metric we defined so far. It doesn't take into account the size of the network or the size of the infection. If a network is large, then a node might have greater importance value under our definition than one in a smaller network due to more terms being summed, as we can see from node 3 in these networks. Additionally, in the same network, the size of the infection itself can affect the centrality value. Larger infections can lead to larger centrality values just because they're more percolated nodes to start from, and therefore more non-zero summons in the centrality calculation. All of this means that we're not just measuring node importance with our metric, we're also measuring network and infection size implicitly. It would be nice to normalize this metric for the size of the network and the size of the infection so that we always get a number between 0 and 1 that tells us solely about the importance of a node V, with 1 meaning as important as possible and 0 meaning not important at all. To accomplish this, we can redefine importance as our original result divided by the maximum possible value of our sum. So, what is the maximum possible value of our sum? Well, the maximum occurs when our node of interest, V, is present along all percolated shortest paths in our network of n nodes, meaning the fraction in our sum will always be 1. This means our sum turns into a sum of node percolation values. If we let P of t be the number of percolated nodes at time t, and remember that each percolated node S has exactly n-2 targets R, then our sum's maximum value is P of t minus 1 times n minus 2 if our node of interest is percolated, or P of t times n minus 2 if our node of interest is not percolated. We can condense this into one expression as shown here. Feel free to pause the video and convince yourself that this captures the case where V is percolated and where V is not percolated. We can further rewrite the left factor in this expression as the sum over all nodes I of x sub I of t minus x sub v of t, as the sum of the percolation states of all nodes at time t will be P of t, so long as we're only allowing binary node percolation states of 0 or 1. We can now divide our original centrality measure by this number to get the percolation centrality most commonly seen, which we'll refer to as Pc of Vt, standing for percolation centrality of node V at time t. We can also refer to it as Pc of V if it's understood from context what point in time we're considering for our network. We now have a nice metric of node importance in networks undergoing some kind of percolation process, which outputs a number between 0 and 1, where numbers close to 1 mean the node is important. Moving on, let's look at some examples to build our intuition. First, let's take a look at the case of a network with a single percolated node. In this example, the percolated node B has just one neighbor A, so A will have percolation centrality 1. This is because 100% of the shortest paths that start from the percolated node pass through A, and the only non-zero x sub s is x sub b because B is the only percolated node. So the sum in the numerator will equal 8, and the denominator will equal 1 times 10 minus 2, which is also 8. As we get further from our single source of infection, our percolation centralities decrease, as there are fewer percolated shortest paths passing through each node. Also, note that the percolation centrality of the single percolated node B is 0. Note that if instead A was the only infected node, then even though B is a neighbor of A, it has percolation centrality 0 because excluding the percolated shortest path from A to B, none of the other percolated shortest paths in the network pass through B, so all of the summons in the numerator of its percolation centrality calculation are 0. The rest of the node's percolation centralities remain the same as before. Next, let's think about percolation centrality for any node V at a fixed time in a fully percolated network. In this case, all of the weights x sub s are equal to 1, which means the left factor in the denominator is equal to n minus 1. We're left with summing over all ordered pairs of nodes the fraction of shortest paths that pass through our node of interest, and then dividing by n minus 1 times n minus 2. Do you recognize this new expression? It's nothing more than the expression for betweenness centrality in a directed network, which is one of the most common metrics of node importance that considers the most important nodes to be those that appear in a large fraction of shortest paths between ordered pairs of vertices in the network. Here are the percolation centralities, equal to the betweenness centralities of all our nodes. Moving on, here's another way to think about the connection between betweenness centrality and percolation centrality. If we let an infection spread in the following network, notice how the percolation centralities of the nodes on the left begin very different from their betweenness centralities displayed in the network on the right. But as the infection nears completion, the percolation centralities approach and eventually equal the betweenness centralities. This shows us that percolation centrality gives us the most novel information that could not be obtained from analyzing the structure of the network alone during the earlier stages of infection. Next, let's look at one last connection between percolation centrality and betweenness centrality. With node B as our node of interest, if we start an infection at each node that's not B in this network, and sum the percolation centralities of B for each case, and then divide by the number of cases, which is 6 in this example, we get the betweenness centrality of B. In other words, the average one-point source percolation centrality of B equals the betweenness centrality of B. Now, it turns out that the average one-point source percolation centrality equals the betweenness centrality for all nodes in this network. We can also take this a step further. It turns out that this is true for all nodes in any network. Here's why this is true. If only one node W is percolated and our node of interest is V, then the left factor in the denominator will equal 1, so the denominator becomes n-2. Also, the summons with source node not equal to W are all 0, and the summons with source node equal to W are all equal to the shortest path fraction. So if W is the only percolated node, then the percolation centrality of V is 1 over n-2 times the sum of the fraction of shortest paths that pass through V, which start at W and end in some other node R. Taking the average over all n-1 choices of percolated single nodes W, we get the betweenness centrality of V. Moving on, what if we allow for partially percolated nodes? That is, we allow nodes to be percolated to a degree from 0 to 1. It turns out that thanks to the way we've written our expression, we can use the same expression to give a nice definition of percolation centrality when we allow for partially percolated nodes. In our expression, the numerator is still a sum of fractions of shortest paths, where we now allow for weights other than 0 or 1. Intuitively, we're saying that paths that start on nodes that are heavily percolated, with weights close to 1, are more relevant to the spread of infection than paths that start on nodes that are lightly percolated. The denominator is still the maximum possible value of the sum in the numerator, so we still get a final output between 0 and 1. To see why this is, notice that summons corresponding to non-percolated source nodes are still equal to 0, and there are still n-2 summons for each choice of source node. And if the shortest path fraction is maximized to 1, assuming our node has a place along every percolated shortest path, then each of the n-2 summons will equal 1 times x sub s of t, meaning they sum to x sub s of t times n-2. From here, it's straightforward that our denominator is the maximum possible value of the sum in the numerator for any node in any network. Here's an example of a network with partially percolated nodes, where nodes 1 and 2 have percolation states 0.8 and 0.7, and nodes 7 and 8 have percolation states 0.4 and 0.3, with all other nodes not percolated. Despite the fact that nodes 3 and 6 are symmetrically positioned with respect to percolated nodes, the fact that 3 is close to heavily percolated nodes and 6 is close to lightly percolated nodes results in a higher importance value for 3. Moving on, let's think about how percolation centrality can be applied. Whatever the contagion is, whether it's a computer virus, a biological virus, or a rumor of some kind, percolation centrality can tell us where we should allocate our resources to stop the spread. If we can only intervene at a limited number of nodes, it would be a good idea to intervene at the nodes with the highest percolation centralities. In this large network, where there are always edges going in both directions between adjacent nodes, where the infection states are binary, and at each time step the infection spreads at a probability of 25% through each edge, let's look at what happens if we protect the 3 non-percolated nodes with the highest percolation centrality versus if we protect the 3 non-percolated nodes with the lowest percolation centrality. Note that in this case, the 3 nodes in green that we selected with highest percolation centrality are not the same as the 3 nodes with the highest betweenness centrality, although there's overlap. Watch how much slower the infection spreads on the left with a percolation centrality-based intervention than it spreads on the right, where we intervened at nodes that had a low percolation centrality. This won't always be the case because there's an element of chance involved, but simulations have shown that percolation centrality-based interventions are effective and are most effective relative to other interventions when the infection has established itself to some degree but is still in the early stages. That's it for this video. Thanks for watching. If you enjoyed this video, please subscribe and click the like button. Have a great day.